This is problem 15. Again, this is the resource page. It's clickable here, or I posted it in Classroom. So we're going to use what we did with inverses yesterday to continue and talk about graphs of inverses. So make a careful graph of each function's inverse on the same set of axes as its corresponding function. Look for a way to make the graph without determining the equation of the inverse first. Be prepared to share your strategy with the class. So sure, here on this equation, y equals 0.5x plus 3, we could write the inverse. We could write the inverse on this second one, but this third one, when it's y equals 1/6 x cubed minus 13/6 x plus 2, we don't know how to write the inverse for that equation yet. So we're going to try to do all of these without writing an equation. So what I'm going to have us do is make a table for the points that are already plotted on here. So on this first one, let me zoom in a little bit for us. We have the point -6, 0, -4, 1. We have this point here at 0, 3. We have the point 2, 4. So again, I'm just putting these in a table. Then we have the point 8, 7. Okay, so this is my resource page. I wrote my points in a table. Again, I just took these points in the graph and put them there. So if you remember what we did yesterday, and I'll kind of flip back to show us, this was problem 5-2 for a function and its inverse. The point 3, 7 was our original, and then 7, 3 was the inverse. 4, 9 was the original, and 9, 4 was the inverse. -3, -5, and then that became -5, -3. So for our inverse here, we're just going to switch the x and the y. So -6, 0 is going to become 0, -6. -4, 1 becomes 1, -4. 0, 3 becomes 3, 0. 2, 4 becomes 4, 2. And 8, 7 becomes 7, 8. So we can go ahead and plot these points now to get the graph of our inverse. So again, instead of writing the equation, which we could do here, I just put these points in a table, and then for my inverse, we switch the x and the y. So you're going to do the same thing down here on this second graph. And one thing I actually want to point out on this problem, so a linear equation, the inverse is also linear, but one thing people get confused on, these both have a positive slope. People tend to think that, well, if this one's positive, the inverse has to be negative, and that's not the case. These both have a positive slope. All right, so again, we're just going to write the points here on the second one. So -4, 6, -3, -3, -2, -6, -1, -3, and 0, 6. So see if you can make the table for the inverse and then also sketch that graph. I'm going to give you, I don't know, 30 seconds to a minute to try to get that going. I switched my X and Y's and then I plotted those points. And so this kind of gives you an idea. Hopefully you can see what it looks like here. And we're going to have that kind of sleeping parabola. And then there's this last one here. Again, we couldn't write the inverse for this equation right now. We haven't gotten that far, but we can graph it. So again, just put these points in a table. So I'm just flipping all of these. And then go ahead and plot them. So this one might be a little bit harder to see kind of what the graph looks like. Maybe it's not. So again, get those points plotted. Some of these kind of get busy in here because there's a lot going on. This point repeats because the X and Y coordinate were the same. So this one, It's going to look like that. So that was 15, all part A. For part B, it says describe the relationship between the coordinates of a function and the coordinates of its inverse. Use tables of the function and its inverse to show what you mean. So basically just kind of what we did, I'm going to write it in words. The X and Y values switch in a table. For a function and its inverse. So X and Y values switched in a table for a function and its inverse, just as we saw here. On problem number 16, it says when you look at the graph of a function and its inverse, you can see a symmetrical relationship between the two graphs demonstrated by a line of symmetry. So we can see that there is some symmetry hopefully going on. It's kind of the same graph, just turned sideways for all three of these. All three of these have a line of symmetry. So remember that line of symmetry, what that means is where could you essentially fold this graph in half so that it lands on top of itself. So if you figure it out, awesome. So what I want everyone to do is kind of try to take a minute, try to see where kind of that line of symmetry is. Don't say it in the chat just yet. If you get it for this first graph, try it for the second graph, then try it for the third graph. Are the lines the same? Are they different? Are they similar? Where can you fold this graph? And try it, actually fold your paper. There's no harm in folding your paper. And then you want to see kind of, how do I get this point to land on this point? How do I get this point to land on this point? This point has to land on this point. So try to figure out if you could sketch in that line. We'll draw it in a minute. Do it in pencil. See if you can figure out where the line of symmetry is for all three of these graphs. Again, so the line of symmetry goes through 0, 0, 1, 1, 2, 2, 3, 3, all of those. If it's the point is the same for a function and its inverse, it's on the line of symmetry, like here and here, here on the first one. So now we want to write the equation for that line. I started kind of the sentence here. The line of symmetry for a graph and its inverse is, we know it's linear. We know it's y equals, in the form y equals mx plus b, because it's a straight line. So if we're looking at this red line here, y equals mx plus b, we see our b value is 0, and we see that our slope is 1 over 1. So our equation here is just y equals x. slope of 1, y-intercept of 0. That's the line of symmetry. And hopefully that makes sense because we were just switching our x and y values. So if y equals x, we just kind of flip them over that line so that we can switch them. All right, so we're done with those resource pages. We'll go to the way. All right, so on problem number 17, it says you can use the line of symmetry to help graph the inverse of a function without creating a table. So rather than creating a table, we could have used that line of symmetry and folded over it. So what we're going to do here is make a complete graph of y equals x over 2 squared. It says on a full sheet of graph paper, use the same scale for the x and y axes. So you are not making a little tiny graph. I'm going to use kind of, it needs to be a somewhat big graph. Doesn't necessarily need to be the whole sheet, but you're not making a tiny graph. If you need to flip the page because you're at the bottom, then flip the page and you could use the rest of this space later. We'll just set up axes. Mine looks like that. So it says use the same scale for both of these. So I'm just going to count by ones. If you want to count by twos or by 1/2, maybe I'll count by half. I don't quite remember. It doesn't really matter as long as you're being consistent. So off to the side, I am going to make a little table. And I'm not going to use it to make my inverse. I want to avoid that, but I want to kind of figure out where these points go. I'm going to also count by even numbers. Because I'm dividing by 2. That way I can help avoid fractions. So again, I'm only making this table to help me plot this graph. So if I plug in -8, -8 divided by 2, I get -4. Squared, I get 16. -6 divided by 2, I get -3. Square it, I get 9. -4 divided by 2 is -2. Squared, I get 4. -2 divided by 1, or sorry, divided by 2 is -1. Squared, I get 1. 0 squared is just 0. And my table will repeat. So plot those points. Again, I'm just going to count by ones. My point for 16 doesn't quite fit on my graph. So once you get that drawn, your parabola, you want to draw in the line of symmetry. Remember, the line of symmetry is always going to be y equals x for any of these. So it goes through 1, 1, 2, 2, 3, 3, 4, 4, 0, 0, -5, -5, -9, -9, so on. So you're going to draw in that line of symmetry. So once you get it in, what they want us to do, and it's going to be a little bit trickier. One, we usually do this on, I do it on a loose piece of paper, and two, it wants us to use a pencil or a crayon. So what you're going to do is trace your original curve with your pencil or crayon until it's heavy and dark, and then fold on your line of symmetry. So you're going to trace this parabola. Again, the idea, what you're going to want to do here, and hopefully it works, is fold your paper on this line of symmetry so that, and then press it so that you'll be able to get the graph to rub off on the other side. Crayons work well if you have them accessible. I did not get any crayons out ahead of time. Some gel pens work that kind of smear easily because the ink doesn't dry right away. Again, you're tracing this. And then you're going to fold your paper on that line of symmetry. Best that you can in a notebook. And then ideally what you want to do is rub it really hard so that you can get it to transfer to the other side. So you can kind of see where mine is here by where I traced it. I know it's very faint because it's on the other side of the paper, but you want to rub that so hopefully it will transfer to the other side. And again, you can trace it darker if you need to, now that you kind of know what we're doing with it. And it is very faint on my paper. I don't know if the lighting even lets you see it, but you can see, I can see it. It's right here. Were you guys able to get that to work? Anyone? Was anyone successful? Yes, no, kind of?
It's very faint.
Yeah, just, and so mine was very faint too. Again, it's going to depend on the type of lead or what you're using, and how hard you push, but hopefully you can kind of see the same idea. And that's how we can use that line of symmetry also, especially if you don't have nice coordinates that it goes through, that'll help you there. So for 5-18, if you have space kind of at the bottom of the graph, that's fine because it's referring to this same graph. And we want to talk about the domain and range of these. So I'm just going to put it down here. So for our equation, y equals x over 2 squared, we want the domain and we want the range. So our original graph that we had here, this original parabola, this one, the domain is all the x values. So our domain here is all real numbers because it goes left forever and right forever. And then our range, remember, is our y values up and down. And so the lowest it goes is 0, and it touches 0, and then it's going up forever. So our range is y is greater than or equal to 0. Then we have the inverse, which is this guy. That we also have to write the domain and range for. See if you can write the domain and range for this inverse. Domain, remember, is x and y. How far left and right, or sorry, domain is x, how far left and right does it go? And range is y, how far down to how far up does it go? So your domain here should be x is greater than or equal to 0, because it goes left, it stops here, then it goes right forever. And then our range is how far down does it go and how far up does it go. So it goes down forever and up forever. So our range is all real numbers. So for part B, how are the domain and range of the original function related to the domain and range of the inverse? So here's our original, here's our inverse. What happened to our domain and range here? So the domain and range switched. Yeah, they're flipped. They switched. Here the range was, domain was all real numbers, so then the range becomes all real numbers. y is greater than or equal to 0 was the range. So the domain is x is greater than or equal to 0. Remember, domain is x and range is y. So they switched, and then x and y also have to switch there too. All right, I'm gonna flip the page. We're skipping problem 19 and we're gonna do 20 and 21, which essentially kind of refer to this same problem. So keep it in mind for what's going on. I'll flip the page back when necessary. So we have this equation, y equals x over 2 squared. And you need to write the inverse of that equation, just as we were doing yesterday. So there's a couple of different ways to do this. If you're good at algebra, and this isn't what we did yesterday. Let me talk about what we did yesterday is we would write out the steps. So remember, the first thing we do here is divide by 2. And then the second thing we do is square it. So for our inverse, remember, you do the opposite in the reverse order. So you would undo those steps in the reverse order. Oops, let that focus. Another way to do this problem is you can switch x and y and then solve for y. And I'll show you that way in a minute. Actually, I'll show you that way now. So define the inverse. This is another option. Switch x and y, which we talked about. That's what happens for a function in its inverse. The tables switch. So we switch x and y and solve for y. And if your algebra skills are not super strong, this isn't the method you're going to want to do. You can do this method. You can write your steps, you can reverse them and do the opposite and get the equation that way. So to do this way, again, we switch x and y, and we would solve this for y. So I would have to square both sides, or square this side, so that'd be y squared over 4. I would multiply both sides by 4 to get y alone. Have 4x equals y squared. And then to get this by itself, I'd have to square root both sides. So y would equal plus or minus the square root of 4, we know is 2. And we don't know the square root of x. Just like here, if I were undoing this squared would be the square root. And then undoing dividing by 2 would be to multiply by 2. So my inverse would be y equals the square root of x times 2. And what you want to be careful of here is you still need this plus or minus. Because if we think way back, we should remember that a square root graph a square root graph looks just kind of like that. So we also need the bottom half of it, which would be why we have a plus or minus. And anytime we undo the square root, really this should have the plus or minus right here, just as it shows up there. So again, this is what we did yesterday. We flipped the steps. You can also do it algebraically by switching x and y. Both ways, you should get to the same answer. So that's our square root graph, and we need the bottom half. All right, so 5-21, last one, still referring to that same problem. So consider the equation for this inverse. So consider this, which is the graph we graphed here, the sleeping parabola. There it is. So that sleeping parabola there, is it a function? So the inverse, which is this thing, or this guy, is not a function. And we can tell by looking at the graph, it's a sleeping parabola. We should know sleeping parabolas are not functions. I should write because some inputs have multiple outputs. Remember, to be a function, every input has to only have one output. It has to be unique. So B says, I'm going to write the directions here in case you trace over the original for which x is greater than or equal to 0. So they want us to trace over the original graph when x is greater than or equal to 0. So I have to flip the page back. I'll give you a second. You don't have to necessarily write that down. I'm going to actually highlight it. So for when x is greater than or equal to 0. So the original graph when x is greater than or equal to 0 is this part.
More burn, but it's like.
So what part of the inverse would that be? Would that be the top half or the bottom half? I have a few people chiming in. So think about when I fold this, it's harder to see now. But remember, a point in its inverse here have to be the same. So that yellow part would correspond to what I'm going to highlight in pink then. So it gives us the top half there. Thank you to the same 4 or 5 people responding in the chat. Most of them are private, but I still appreciate it. So it's the top half. So the equation for that top half is the positive part of this. So the equation that I highlighted in pink, just this part, would be y equals 2 times the square root of x. So we restricted the domain. I should have put of the original. So right here, we restricted this domain. Instead of all real numbers for x, we only looked at half of it. By only looking at half of it, we only look at half of the inverse. And this pink part here is, sorry, can't see it. This pink part is a function. So by only looking at half of the parabola, when we do the inverse, we still have a function. If we have a whole parabola, the inverse is not a function. It's still the inverse, but not a function. If we take half of it, we have a function. We could have taken the other half also. We could have done the bottom half or the left half, which would be the bottom half, and we would have a function. So by restricting that domain of the original, so we're only looking at half of it, then it's an inverse, or the inverse is a function. And like I just said, if we looked at the other half, if we did y equals x over 2 squared for x is less than or equal to 0, then the inverse would just be y equals -2 root x. It would be the negative part of it. It would be the bottom half if we looked at the left half of the original. Okay. That is it. So just to kind of recap what we did, we talked about, we reviewed that resource page, we talked about a function and its inverse, the x and y tables switched, we made that line of symmetry, the domain and range also switched, that line of symmetry is x equals y. Not every function has an inverse, but the inverse is not necessarily a function. To make it a function, we have to restrict the domain on some of them so that when we reflect it across that line of symmetry, we still have a function. Your homework tonight, just to make sure you're paying attention, it jumps around. I think it was like 26 and then, what is it, 32 to 34, 37, 38. Make sure you're doing the problems that are assigned. Some of them won't make sense if you try to do the other ones anyways. But that is all we have. You are free to go unless you have questions. I will see you tomorrow.